Okay, welcome to lecture 39, and in this lecture we'll learn about Poisson brackets, some mathematical quantity which has very important role in studying classical mechanics. And last few lectures, let me recap just in 1 minute. So in last few lectures we have learned the Hamiltonian formulation. Initially we learned Lagrangian formulation, which gives you second order differential equation, and in the Hamiltonian formulation we found that it has first order differential equation, which are known as canonical equation, and but the numbers are double, and you have the underlying space is the phase space, which is double in dimension of the configuration space. If configuration space is n dimensional, then phase space will be 2n dimensional. So Lagrangian and Hamiltonian formulation we have learned. So we know how to calculate the Lagrangian, Hamiltonian for simple systems, and then how to find equation of motion and to find solutions of this. Now when we try to find the solution means in classical mechanics, solution means you have to find all position, that means all coordinates at a different time. So how the coordinates or how the system evolve with time, that you have to find. That means you have to find the dynamics of each and every quantity associated with the system. If some of the quantities are not change with the time, then it is easy for us. If some of them are constant, does not change with the time, so we don't have to calculate their dynamics, they are always constant. So constant of motion is very important in the study of classical mechanics. So constant of motion is very useful in finding the, because we don't have to find dynamics, finding the dynamics of the system. For example, if some x component momenta is constant, then it is constant, then it's you can write mx dot equal to constant, and you can find a solution very easily. Okay. That is why we have learned cyclic coordinate. Cyclic coordinate gives to the constant of motion, and also the symmetries gives the constant of motion. Now we'll see so it is important to find constant of motion in the theory. So now let us see a quantity you have, a dynamical or a observable you have f, which is function of say qi dot t, or in the Hamiltonian formulation we consider this as function of qi, pi and t, and we are interested to know whether this quantity is constant or not, or under which condition it will be a constant of motion. So constant of motion means this total time derivative of this quantity will be 0. So let us calculate this quantity. So if we calculate this quantity, we will find if it has a time dependence, so del f del t. If it doesn't have any time dependence, then del f del t will be 0. Then using differentiation chain rule, I can differentiate with respect to qi, then qi should be dot, and this should be sum over all I equal to 1 to n if you have n degrees of freedom. Then you have the other variable del L del pi and pi dot, okay, and again sum over, so this common summation I am using. Now remember canonical equation of the system. Suppose the system has the Hamiltonian qi, pi and t, and in that system we are looking for under which condition and when f can be a constant of motion, okay, or it will not evolve with time. Okay. So you use the canonical equation, qi dot is del h del pi and pi dot is minus del h del qi. These are canonical equation. Okay. So, if this canonical equation I use in the expression, say let us denote this equation 1 in the expression of df dt. Okay. So, this let me write df dt. So, what we will find? So, df dt I will find del f del t plus sum over I 1 to n del f del q I and q I dot is del h del pi, okay, and second term del f del pi and pi dot is minus. So, that is why I wrote minus del h del q I. Now, we are looking for a quantity which is constant of motion or not. So, first we will see whether it is explicitly depends on time or not. If it is explicitly depends on time, there is no need to search for constant of motion with that quantity, because a quantity which explicitly depends on time cannot be a constant of motion, right. We assume that okay, it does not depend on explicitly on time. So, let us assume that del f del t equal to 0. So, in that condition, that situation df dt will be 0 if and only if that del f del q I sum over all I equal to 1 to n del h del pi minus del f del pi del h del q I equal to 0. So, this quantity is defined as the Poisson bracket this quantity is defined as Poisson bracket f with h with respect to variables qi and pi. Qi and pi are canonically conjugate variables. So, what is the definition of Poisson bracket? Suppose two variables f which is also pi, qi and t, and g another variable qi, pi and t. So, the Poisson bracket, let me write in short, Pb of f and g is then defined sum over I. First one should be differentiated with respect to qi, second variable will differentiate with respect to pi, minus now first variable f should be differentiated with pi and second variable should be defined with respect to qi. So, this is denoted as Poisson bracket, and the symbol for Poisson bracket is the middle bracket we write. So, f and g and with respect to variables qi and pi, this is important. So, this Poisson bracket, so using Poisson bracket we can say a quantity will be conserved. So, a quantity which a quantity does not depend on time explicitly, will be constant of motion if its Poisson bracket, say quantity, let us say f, its Poisson bracket with the Hamiltonian will be 0 with respect to the canonical variables. Okay. So, the Poisson bracket, idea of Poisson bracket is important to find the constant of motion in a system, and it has a very important structure in the Hamiltonian formulation or in the formulation of classical mechanics that we will learn slowly. So, first thing is that the canonical equations of motion can be written in terms of Poisson bracket. So, how q I dot is del h del p I. So, which I can write as Poisson bracket of q I with h. How? So, let us calculate this Poisson bracket. So, q I dotted with q j and del h dotted with j p j, sum over j. So, I am writing the definition of Poisson bracket minus q I differentiate with the p j, but q I and p j are independent to each other. So, del h del q j, but this term is 0 because q and p are independent. So, this, and then you will find that del q I q j will be delta I j of del h del p j sum over j. So, this is nothing but del h del p I. So, we have written that q I dot is basically q Poisson bracket with this and with respect to q and p. So, unless otherwise it is not mentioned, we have always the Poisson bracket in terms of the q and p. So, when we will have more set of canonical variables, we have to mention with what canonical variables we are defining Poisson bracket. Similarly, in a straightforward manner, you can see p I dot is also p I h. Okay. So, the canonical equations can be written in terms of Poisson brackets, and also you see this is very symmetrically written. Earlier canonical equation q I dot does not have minus sign, but p I dot has minus sign. So, here it is both are in the equal symbol, both the Poisson bracket with respect to Hamiltonian. Now, let us, so it is important to study classical mechanics to calculate Poisson brackets. So, let us see some properties of the Poisson bracket. So, I will list down the properties of Poisson bracket. So, and later we will verify those. So, f g Poisson bracket will be minus g f. So, if we interchange order of the variables, there will be a minus sign, and it is straightforward from the definition. First term will go to the second term and second term will go to the first term. So, you can very easily see these properties. Now, second property is that if you have the Poisson bracket with respect to two different quantities g 1 plus g 2. So, it is basically the Poisson bracket of f with g 1 plus Poisson bracket of f with g 2. So, this Poisson bracket of sum of two quantities is the sum of Poisson bracket of those two quantities. Now, for product properties 3, if you have a product of two quantities g 1 and g 2 and Poisson bracket you are calculating for f, then it will be the differentiation rule also will be followed, f g 1 Poisson bracket with g 2 plus g 1 f Poisson bracket with G2. Okay. So, we will verify explicitly these properties, and then if you have a differentiation of a Poisson bracket between f and g. So, this del f del t with g plus f with del g del t. So, these are very straightforward Poisson bracket properties, and lastly I will mention a very important properties and which is called Jacobi identity. So, Jacobi identity of Poisson bracket. You must have seen the Poisson Jacobi identity for the matrix multiplication. Now, Poisson bracket also satisfy Jacobi identity. So, let me write this Jacobi identity and then I will explain. So, if you have three variables f, g and k. So, suppose you take a Poisson bracket between g and k, and then this Poisson bracket has a Poisson bracket with respect to f, and all are in with the variable q and p. So, only canonical variables in the theory. So, f and g. So, then keeping the bracket structure same, if I permute this in a cyclic fashion, so bracket structure will be like this. Now, I permute, so g will come now. So, g, then k Poisson bracket with f. So, bracket structure is same, then g, now k will come, k and then f and g, and this will be 0. So, this is the Jacobi identity. So, what is Jacobi identity? Keeping the bracket structure, Poisson bracket structure same, you permute the three variable in a cyclic way, and then sum of these three term will be 0. So, we could have taken the bracket structure like this, that f, g and then its Poisson bracket with k plus cyclic, this also will be 0. So, whatever bracket structure of a complicated this three variables Poisson bracket, you first mention, and keeping that structure same, if you have a cyclic permutation, then you will have adding up those three terms, it will goes to 0. So, this is Jacobi identity, and Jacobi identity has a very important role in physics. In many places we should learn Jacobi identities. So, now let us verify these properties. Verification of Jacobi identities involve lot of algebra, but I will tell you how to verify the main steps to verify Jacobi identity. So, let us consider the case of product rule. First two rules are very simple and straightforward. You just put in the formula, you will get. Now, let us consider the properties 3. Properties 3 is f and g1 g2. So, this Poisson bracket. So, let me write and assuming that only one variable, just only one q and one p to minimize the algebra. So, del f del q, then del p of g1 g2 minus del f del p del q of g1 and g2. So, simply you just make the differentiation rules for product variable, you will get the properties. So, first del g1 del p and g2 is unchanged. Let me I should not use middle bracket for this section, at least will be used for the Poisson brackets, plus g1 del g2 del p. Similarly, second term, and it will be del g1 del p of g2 plus g1 del g2 of del p. So, now you can combine. Suppose if you combine this term with this term, you will get a Poisson bracket f g1 and outside is g2. Similarly, if we combine the other two terms, you will get g1 and then Poisson bracket of f g2, okay, which proves the identity. Similarly, if you have a time derivative, that del t of f g, that property is 4. So, this you will have, that, okay, let me write again, I will simplify with one variable, one set of canonical variables. So, del t del f del q del g del p minus del f del p del g del q. Okay. Now, this is a partial derivative with respect to time. So, we can think of that you can interchange the order of differentiation. So, we can write this as del t of f q first, and del g, order of differentiation will change later, then del f del q del t of del g del p minus del t of del f del p del g del q unchanged minus del f del p del t of del g del q. Okay. Now, if you interchange the partial derivative and the differentiation with respect to q and p are interchangeable, then you can find that equal to del q of del f del t from the first term and del g del p, and let us combine with the term this term. So, this term and this term. So, minus del p of del f del t and del g del q and other two terms. So, if we combine the remaining these two terms, I can find this is nothing but a Poisson bracket of del f del t with g. Similarly, other two terms will give you the Poisson bracket between f and del g del t. So, this proves the partial differentiation of this properties 4, that when you partially differentiate with f t, then this you can get the. Now, let us talk about the Jacobi identity. The proof is little bit lengthy, but let me tell you how to proceed. So, let us consider the Jacobi identity f. So, f comma g k, this Poisson bracket, plus g comma k Poisson bracket with f will be minus of the last term. So, minus it will be minus, it will be k Poisson bracket with f and g. Okay. So, let us write this is equation 2. Okay. So, this is I have written the Jacobi identity, and just third term I have shifted to the right hand side. So, now let us calculate this two term and try to see whether we get that term. So, there will be lot of cancellation and to achieve that result, but let us do this. So, if you have, let me write del f del q times del f del p of g k Poisson bracket minus del f del p del q of Poisson bracket g k. Okay. and then plus del G del Q del P of Poisson bracket K comma F minus del G del P and del Q of Poisson bracket K comma F. Okay. So, this is the left hand side of this identity we are studying. Okay. So, now I will further break. So, there will be 4 terms. So, this will produce 16 terms because let me tell you these 16 terms, the nature del F del Q and then del P of del G del Q del K del P minus del J del G del P del K del Q. Okay. This, so from the first term we get the product of 2 and product of 2 with the differentiation. So, let us simplify this term. So, we can get idea of the number of terms. So, if I differentiate this, I will get del 2 G del P del Q and del K del P first term, second term will be plus del F del Q del G del Q and del 2 K del P square. Okay. Then 2 terms from this minus part, second part del F del Q and then del 2 G del P square and then del K del Q minus del F del Q and then del F del Q and then you have del G del P del 2 K and del P del Q. So, this 4 terms coming out of this first term. So, you will get total 16 term. So, I suggest that you collect all these 16 terms and then there will be cancellation. So, I will tell you that what are the terms to be cancelled and the remaining term you construct in the Poisson bracket and you will get the right hand side. So, if you look at the right hand side we had, so which term we are expected to cancel. So, if you have K, let me see the right hand side, K and then FG, K Poisson bracket with FG. So, this is the term you are supposed to get. So, let us this also will give you 4 terms, right. So, it will be del K, quickly let me write del K del Q del P F and G minus del K del P del Q of F and G. Okay. So, this term, so 4 and 4, so there will be 8 terms here. But notice in these all 8 terms, all having the first derivative, the derivative order, derivative of K is only the first order. That means, it will be always del K del Q or del K del P. There will not be a single term which non-vanishing term with del 2 K del P square, del 2 K del Q square or del 2 K del Q del P. These 3 type of terms will not appear. So, in this 16 term, see here you have a del 2 del P square. So, this term should cancel, there this term should cancel and only first derivative of K terms will survive. So, if you collect, there will be 16 terms I said. Among those 16 terms, look for these terms which will be cancelled and then you will remain with the 8 terms, and those 8 terms if you combine your thing, then you will get the Jacobi identity. So this proof I hope you can do yourself with these hints, and you should do with at least one set of canonical variables. It will be much more complicated with the many canonical variables because there will be summation involved. So I am not suggesting to do that. Next class it will be a tutorial class, and in the tutorial class we will consider some example or application of Jacobi identity. Okay, so bye for this class. Now in next class, which will be a tutorial class, we will solve some problems on Poisson brackets and find its usefulness. Okay, so bye for now.